Is my presentation visible?
Yes, we can see your presentation.
Yeah, okay. Good afternoon, everyone. I'm Sanjeev, and here's Shadab with me, and we'll be presenting on the topic deep reinforcement learning-based controller for navigation of an autonomous ship today. So first, we'll briefly do a recap of what we covered in the previous presentations, and then we'll look at the latest results, and we'll see how the comparison of the RL-based controller looks compared with the PID controller, and then we'll look at another RL algorithm called the DDPG algorithm. So, like Shadab can go on.
So hello everyone. In this slide, we have two coordinate systems. First is the body coordinate system, and second is the global coordinate system. So in the figure, you can see that size the heading angle defined as the angle between the positive x-axis of GCS and BCS, whereas the beta is the drift angle. It is defined as the angle between the velocity vector and the longitudinal direction of the ship. So,
Shadab, we can't
yes,
see you somehow.
Oh, okay, sir. Sir,
Yes, we can see you now. Yeah.
so below you can see these three equations. These equations are the forces that we are encountering on the ship. So here M is the mass of the ship, mx is the added mass. This xg is the distance between the body coordinate system origin and the center of gravity. The generally origin of the BCS is located at the intersection of the midship, center line, and water line. R is the change of this side. So can you go to the next slide? So the forces that are present are divided in are further classified in this hull forces, rudder forces, and the propeller forces. So these equations help us to divide those. Next slide. Sanjeev, can you go to the next slide? Yeah. So now the rudder angle is governed by using this first order equation. In a practical scenario, the rudder angle cannot be varied instantaneously. So here delta dot is the rudder rate, delta is the actual rudder angle, while delta C is the commanded rudder angle. So here we have given us rudder saturated rate also, that is the minimum of commanded rudder angle minus actual rudder angle divided by rudder time constant, in which we have taken a rudder time constant at 0.1 in our case, while rudder rate maximum value is taken as 5 degrees per second for a full scale model. Can you go to the next slide? Now we have took Q learning. First, we will talk about the Q learning. So Q learning is a fundamental RL algorithm in which there's every action has an associated reward with it. So as here this Q value is denoted by Q S comma A. So A is the action, S is the state. So and you can see in the equation there is a term of pi. It is called the policy of that policy. So the first equation basically tells us about the expected reward that we will get after taking action A at state S and following a policy pi. This Q value is the summation of the reward that we are going to get after taking a reward A at S, and also the cumulative summation with a discount factor of gamma with it for the future values. So next slide.
So can you go back to the previous slide?
Yes.
Okay, so why do we need a discount factor in general?
So we need a discount factor if because if we don't include it, our future means after 1,000 or whatever with the step size will be, means after 1,000 steps also the this reward may have a equal this reward may have an equal weightage on our this next step. Means the step which we are going to take after just the next step is
Okay, calm down first and tell me why is it that we need the discount factor?
is this discount factor is taken as to means as the step the future steps also has the equal weightage as to the preceding steps. Means the step that we are going to take after 10 episodes will have the equal weightage as we are going to take for the next step. That's why
So by giving a discount factor, what am I doing?
sir, you are reducing that value.
Reducing what?
The discount factor is generally lies between 0 to 1, and if you are including that, it means you are more focusing on the current transaction from S to S dash rather than from going to another from for example S dash to S double dash. You are reducing the value from there and more focusing on the current reward that it is.
So current reward has more weightage than future reward.
Yes, sir.
That's what it means, right?
Yes, sir.
And here when we say expected value of return, what does expected value here mean?
So actually, we have taken the stochastic nature of the uh, this, of the learning. So we there are multiple ways through which that particular state can be reached, or they
So
can
what
be.
is stochastic nature here?
Sir, so this equation comes from Bellman equation, but our problem is purely deterministic. In general,
Yes,
it is written as the expectation when when the problem is stochastic.
Correct. So it can be that I may take an action A and I may not end up in one state, but I may end up in different states depending on the stochastic nature of the process.
yes, sir.
Right? But that part is not there in our system, right? In
Yes,
our
sir.
case, it is pretty deterministic.
Hmm.
If I take an action, I know that I will go in only one direction. My dynamics is actually determined. Okay, all right.
So yeah, now we are following here. We are following an epsilon greedy policy. So for here we took a parameter called epsilon. For with a probability of epsilon, we take a random action and try to uh, explore the environment. And with an probability of 1 minus epsilon, we take the maximum q value that is associated with the that particular state. So basically, we are in a position of exploit thing. So so particularly we need exploration because we need to find the new reward that are associated and to update our Q network or Q table. And we need exploration because without this, our agent will continuously random will have a random position at every time.
Okay, here I want to mention that those of you who are listening, whenever you have any question, please feel free to stop the discussion and ask the question. You don't have to wait till the end to ask the questions. Okay. All right. Carry on, Shadab.
I have a
Yeah.
question.
And
Go ahead.
The you said the model is completely deterministic for the case. So, like, is that the say the solving the differential equation? That part is already considered in the or like say the maneuvering equations that we have. That is our deterministic part, right?
Yeah, that is our environment here. So yeah, you know that if you take if you give a rudder of 35 degree, you know after next time step what your next position is going to be with 100% accuracy. That is,
Okay, so that information is going to be used by the model itself.
yeah,
Okay.
So in the sense that if I'm at a current initial state with a certain yaw rate, certain sway velocity, certain heave surge velocity, and a certain position and a certain heading angle, and I take a certain action at that particular step, every time I take that action with that initial condition, I'll always end up in only one and only one state at the next time step. Right? I cannot end up anywhere else. But there may be systems where that may not be true. So these are specifically, let's say, chaotic systems, or where there is some randomness entering your what you call in your system. So let us say that you are considering wind also as a parameter, but that is not coming into your state vector. Okay, so now what is happening, each time wind is blowing differently, even though I take the same action from the same initial state, I may not end up in the same final state every time. My final state may be different depending on where the wind is blowing from, right?
Yes, sir.
Yes, sir.
So that is that stochastic nature of the process which comes into the picture. Or it may be so that my differential equation itself is chaotic in nature, in the sense that even every time I choose my initial condition very close to each other, I may actually end up diverging quite a bit. But that's not quite relevant in this sense, because here the time step is really small, so the deviation will not be very huge. But nevertheless, there can be some such sort of, but over time, over multiple time steps, if I look, my process will evolve me and put me in two different states over multiple time steps. So that is how the so-called stochastic nature comes into the picture. Right? Sometimes you may even think, I try to apply a rudder of 35 degrees, but I may achieve 35-degree rudder with some probability. 50% of the time I'll actually achieve 35 degrees rudder. 50% of the time, even though I want to achieve, I may still be at zero, let's say. That's another uncertainty which you can play around with. So the RL agent allows you to incorporate those uncertainties also. I hope that is making sense. Yes?
Yes, sir.
Right?
So also like the rudder is varying with that first order equation, right? So the rudder is not actually going to be 35 when you command it to be.
So the commanded rudder will be 35 degrees, but the actual rudder will not be at 35. Correct.
So the state will transition depending on actual rudder's position.
Absolutely. You have hit on it on the dot. So suppose the two conditions, the rudder angle was actually different in both cases, then my final state I end up in may not be the same.
Yeah.
Right? Perfect. Perfect example actually. All right. Shadab and Sanjeev, you can go ahead.
Yeah. In our case, we have taken a linearly decreasing epsilon value. So Sandeep, can you go to the next slide? Now, deep Q learning. So,
Hello.
yeah.
Can you go to this previous slide, this epsilon breeding? Yeah, you told epsilon, your epsilon was varying. Like, why is it varying here?
So from the starting, we are giving it complete opportunity to explore, and after it is exploring to a certain means, as the time passes, time step passes,
Okay.
we are reducing the value of the epsilon.
So this means that for some time it will explore and it will find some optimal action.
Yeah.
And once that action is found out, it will then exploit that action.
Yeah, the probability of exploration will continuously be decreasing throughout the time steps.
Okay. Yes.
But why is that important, Shadab?
So firstly because of we have different test point around our ship. So firstly, we want to let him explore and make the Q table or the Q network along with it. And after that, when it's have sufficiently explored, this value of the exploitation will increase and it will find the maximum optimality. Otherwise, it will go on keep wandering.
Now, let us say that in one case, I train an agent with an epsilon greedy algorithm, and in another case, I train an agent with no epsilon greedy algorithm. Every time it chooses argmax of Q. Okay? In the beginning, it doesn't know what it is doing, right?
Yes, sir.
So it will automatically explore and find an optimal path, no?
But without random action, it won't find the perfect optimal policy without it. So,
Sorry, come again? I didn't get you.
So without random action, without exploration, it won't find the perfect action or the perfect policy that it has to take to reach the destination.
Correct. It will find a policy to reach the destination.
Yeah,
It will definitely try to find a policy to reach the destination, but it may not be the most optimal.
Yes, sir. That's the main thing.
Yeah, we may be in a suboptimal solution.
Yeah, we may reach the destination, but still that course is not good for us. They takes some other points.
Correct. And I think a good example for that is when we included your rate or we did not include your rate. We saw some funny examples in that. I am hoping that you will show some of them later on.
Sir, so
yes.
What you told was means just an example that if we choose only argmax all the time, argmax A, so that is just like exploitation, no? So it will exploit every time.
It will try to exploit whatever it has found so far.
Found so far, okay. So
right.
the random action that it takes is just to see whether what other actions might provide it. It may provide some greater reward.
Correct. So,
in the
yeah, go ahead.
In the future slide, you will see that there are random points that we have taken in the ship length from 8 to 28, out of which we have individually take one particular point at each time and train that model according to that and that. So this random action makes that thing to happen.
No. Random action of this one is not due to that. That has nothing to do with this. That is generating of the training data. That is what. So let's say that you have a you give a waypoint and you have an initial waypoint. So you have to go from the initial waypoint to the final waypoint. Now, one might want to go in such a manner that you are reducing the distance to the waypoint. The other might be you might want to reduce the so-called sidetrack error or the cross-track error, as however you want to call it. That is the perpendicular distance between the point where you are and on the lines joining the waypoint. I think they'll talk about that as it comes. The other might be you want to be actually heading in the right direction. That might be more important. Right? In an organic sense, when you do a PID control or things like that, what should happen is you should reduce the coarse angle error. You should also reduce the sidetrack error simultaneously. But the agent may have chosen, in the scheme of things that you were training, that it only tries to first reduce the coarse angle error first, which means it's going on a parallel track, but it is off margin. Right? And only at the end it decides to take a turn and come back down. It can reach it like that too, or it could simultaneously decrease both and still reach it. In either case, it is still reaching the target, but one is less suboptimal, one is a better solution than the other. So it is allowing it to explore if there is a better solution than the one it has found so far. So question is whether the one which I found is optimal or is there anything better? If it is suboptimal, can I look for some more optimality in it? That's what it's trying to do. What you are talking about, Shadab, that is the training process. That has nothing to do with the epsilon greedy part.
Yes, for example, if we take our system, our destination points in only the first quadrant, then our model won't learn for the second, third, or for the fourth quadrant. That's what I am saying. That if we are
epsilon greedy, that is not the concept of epsilon greedy algorithm. Epsilon algorithm is coming in when you choose the action, not in choosing the goal point to begin with. While you are executing the actions, if there is one of the points where you are saying that this is my optimal controller, I should apply 35 degrees now, then you are saying, no, 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 with 50% probability, I'll choose a random action between minus 35, 0 and 35. It has absolutely nothing to do with your choosing of the waypoints. That is to generate a balanced training data that has nothing to do with exploration and exploitation. Okay? All right.
So, Sanjeev, next. Yeah. So the problem with the Q network is that the Q values will be large enough if we take a continuous action and it discretize it. So to solve this problem, we use deep Q learning, in which we use a neural network as a function approximator. So here also the value with the maximum Q values is taken and it's executed for that. So basically we are means that here the theta represent the bias and the weights that are associated with the networks, and we have to that we want to reduce the loss function that the optimizer will do it for us. So basically this is the expected reward where the y is the cumulative sum of all the rewards, where r is the reward from going from s to s dash, and gamma is the discount factor which we are talking about previously.
I think this formula might require an update. Sanjeev, am I right? Because this is not considering Q values from the target network being given out, which should be the case.
Sir, this is with the target network. I think Shadab forgot to mention that. So this why target values in deep Q learning, it uses a target network. So the second term, if you see this theta dash represents the parameters of the target network. This will be a copy of the Q network, but its parameters will be updated at a slower rate than the online Q network.
Okay, so y we are getting from the target network. So theta
Yes,
prime represents the target network, correct?
Yes, sir.
And theta represents the current state of the network.
Yes, sir.
Okay, all right.
So
So
why
this
some of the
term it's called the temporal difference, and this loss and the network is updated through gradient descent.
So the obvious question one might have is, why do we need a target network? Why is it needed?
So it helps attain convergence faster. So that is one thing.
So you're kind of updating your network at a slower rate, right? That is the main idea, isn't it, Sanjeev?
Yes, sir.
So that the convergence can be achieved at a faster rate. Because the volatility is less. We are updating the network only every so many number of time steps. So whatever the network is doing, learning and unlearning, the mean of it, in some sense, you're capturing and then updating the target network. So the learning process happens more smoothly over the target network.
Yes, sir.
I didn't quite understand this. Like, can you repeat? Like, after
Sorry?
I didn't quite understand this slide. Can you repeat this slide?
basically in Q network we have a Q table, but for a continuous action this Q table becomes quite big. So to handle this we introduced this deep Q learning, which uses the neural network, and for each network we have a bias and weights associated with it. So that is denoted by this theta value here. So there's the loss function is given by this formula. The y is the this summation of the reward function with the reward function from going the reward from going to s dash, while this max of a dash is the maximum reward that we will get after taking the action a dash.
Okay, so like there is this expected term, right? So in our case, is this deterministic or like, because previously we talked that it was deterministic, right? So whether we'll only have a deterministic term there, or how does it go? Like how
Yeah,
does
in our case, in our environment is deterministic, but in general, you will see an
okay.
expectation. So, because
Expectation.
yeah, from one state, if you take one action, you might not necessarily end up at a certain state.
Yeah.
You might end up in multiple states. So that's why
Sure.
it's expectation.
But does this mean that this expectation here in the loss function is not required?
Yeah, we might exclude it also for our case. It's
No,
12
no. That is very much required. The reason is because you are actually having a replay buffer from which you are sampling a few of the transitions. Right?
Yeah, I have not mentioned it here. So, yeah, so yeah, this is for a single term. This will be there. So in deep Q learning, there is something called the replay buffer. So multiple transitions will be stored, and for updating, a random number of transitions will be selected, and the average of these errors will be taken.
So that expectation is kind of going over the number of transitions which you are taking. So the expected value of the loss over those transitions is kind of your loss function for that episode.
Yeah, the replay buffer basically, so because we select transitions from random, it reduces the bias during the update, provides more stable updates, and data is also reused. So it's data efficient. That is another thing.
And what is this theta dash?
Yeah, so that's what. So in TQ network, so this is called the online network. This provides the Q value. So this theta dash represents the parameters of the target network. As I told, this will be a copy of the Q network, but this theta dash will be updated at a much slower rate than the Q network.
Okay, so that trait is also something we should choose.
Yeah, correct. Yeah,
Okay.
so there will be something called the soft update factor. That is one hyperparameter. Correct.
Oh, okay. And these loss functions, do we have like a library, or how do we implement it?
Yeah, so there are many libraries for like reinforcement learning. So we
Oh,
are using a library called TensorFlow Agents, which is the official RL library from TensorFlow. That's
okay. Fine.
Uh, I what is the like why, for different transitions, why are there different results? So what is the factor that is causing that?
Uh, no, so there's no different results for different transitions. So this expectation is here because this loss usually is computed with not just a single sample, but this loss is computed using multiple samples when the network is going to be updated. So in this replay buffer, like I might be storing the last 10,000 time steps transitions, and maybe I'll select what if my batch size is 100, I'll select 100 transitions from random from the replay buffer and compute this loss, average it out, and use it to update the network basically.
Okay, but those 1,000 will have different SA.
Correct. Yeah. So, this temporal difference will be computed for each single sample, and it will be averaged out. Yeah.
Did that answer your question, Vallabh?
Yes.
Okay. Sanjeev and Shadab, a little pointer. I think the process of the training, if we had covered that, it would have made it much easier for the explanation, I thought.
Yes, sir. I'll go through it soon.
That is included up.
Actually, I haven't still understood this why clearly. Can you please like go through it again?
Yeah, so this is the temporal difference error. So if you see in Q learning, basically this will just be gamma times max of Q of S gamma. So basically it will select the best action from the next state S dash. But in here we use a target network to approximate this value. So,
Yeah. What is the target network? I didn't understand clearly. Means
yeah,
physically.
okay. So okay, so this so okay, we have a Q network that takes in the states and it predicts the Q values for each of the actions that we have discretized for. So this target network, it is an exact copy of the Q network. So it will have the same number of hidden layers. It will be have the same number of hidden layers, the same number of neurons in each layer. And the only difference is that the parameters will be different because this will be updated only once in a while, and this will be updated at a slower rate compared to the Q network.
I think what he's trying to ask is, why do I need it?
Yeah, yes, yes. That is exactly what I want.
Yeah,
Yes.
okay. So yeah, if you do not use a target network, sometimes you might not reach convergence, or it might take a long time for you to reach convergence. So in essence, this target network, it is retaining some memory of the Q network, right? So it will help us attain convergence faster.
May I intervene for a second here, Sanjeev?
Yes, sir.
Okay, so Aditya, think of it this way. You want your network to slowly start figuring out the optimum path or the optimum action it should take, right? Now, every time I take an episode and give it a goal point and ask it to reach the goal point, it will take initially some actions and get there,
Yes.
right? May get there, sometimes it may not get there. And if it gets there, that's a successful episode. If it doesn't get there, it's an unsuccessful episode.
Yeah. Yes.
And all of this data, as it is going through these episodes, right? We're not training just on one episode. We're training it multiple times. We're giving it so many episodes to train.
Yes.
So that data from it. So each time we are having a storage of what state was it in, what action it chose, what reward it got, and what is the new state it went to.
Okay.
Okay, that thing is called a transition.
Okay.
That set of starting state, what action I took, what reward I got, and what is the new state I went to. That's called a transition.
Yes.
So we maintain a table of these transitions
Okay.
over all the episodes that it has maintained, has seen.
So in each episode there will be multiple such steps taken, multiple such actions taken.
Correct. So as many time steps there are, as many transitions there will be.
Yes.
Right.
Okay.
Now what we do, we can't generate infinite number of transitions and hold on to them, right?
Yeah.
So
Yes.
there is a certain limit. So what we do, we create a so-called a replay buffer into which you can think of it as a storage memory in which I'm storing these transitions.
Okay. Okay.
Okay. Then there will be a time when I will exhaust this entire replay buffer. I would have stored everything, the memory will be full.
Okay. So a particular memory will be allotted to this.
So yeah, so I may have chosen, let's say 200 MB, let's say.
Okay. Okay.
Okay, and I would have exhausted that. Then more transitions are coming. As the model is getting trained, I might be having more transitions. So I'll start overwriting some of those older transitions.
Okay.
Okay, now of this replay buffer, which I think in Sanjeev's case is, if I'm not wrong, is 100,000 episodes it can store, or 100,000 transitions it can store. Okay, out of which at a time when we want to update our network, okay,
Yes.
we only choose randomly from this sample of 100,000.
Okay.
Okay, we choose a batch of those. And what he's saying is, when I'm computing that loss, this batch I choose randomly from that 100,000. Right? So I have to take an expected value of it over
Okay.
the number of transitions over which I chose, which means suppose I chose another set. Say suppose I chose 100 transitions to do my update.
Yeah.
And I chose another 100 transitions. They both need not yield the same loss function.
Yes. Yes.
Right? Because
Yes.
I sampled them randomly, and not all transitions are from one episode, remember, because I'm just storing them there and sampling them randomly.
Yeah, they are randomly.
Some transitions from episode 1, some transitions from episode 5, some transitions from episode 5000.
Yeah.
So what he is doing is, at each time he wants to check that whether what the network is predicting as what I should be taking the current step, is it matching with its network's current state?
Sorry, sir. Can you repeat this part?
So the action that it has taken right now to go from S to S prime,
Yes.
okay, is that reward which it has got matching with what the expected value the network should have output.
Okay.
If the network had converged, then these values should be exactly the same.
Yeah. Yes.
If it has not converged, the action I took would be different than the action which would be recommended by the network.
Yes. Yes.
Right? So ideally, in the best case scenario, I want to see that y minus q go to 0.
0.
That is the main idea.
So the action predicted might be the same, but still the Q values might be different.
The action might be the same, but the Q value also might be different. That's also true. He's right. In the sense that if it is in an unconverged state, I may have chosen the same action, but the expected reward I would be getting may not be the same. It might not have converged to the repeating value, which means when the training has not happened sufficiently, I may see that one action is taken, but yet the Q value is not the same as what I expect the next time around. Okay, so that means I should have visited those states multiple number of times in order for the convergence to happen. You're getting my point, Aditya?
Yes, sir. Yes. Like.
Let us say that I start and I have to take a right. I have to take a command to go right. Okay,
Yes.
and I do it only once.
Yes.
Okay, my Q value will be updated to some value, let us say. The next time around I come back to that same state and I take a right turn again, the Q value may get updated from 0.2 to 0.3.
Okay.
That means convergence has not happened. If it had converged, it should be 0.2 only every time.
Yeah. It would not vary.
That is what Sanjeev is trying to tell me.
Yes.
Or modify me or correct me where I was going wrong.
Yes,
Okay.
sir. So one more thing. So yeah, in Q learning, if you see, you will just use that single sample. After you take one action, you'll just take that that single transition and update your Q table. But that's another advantage with the deep Q network you see here, because one single transition can be used multiple times too. So in Q learning, you'll need a lot more training data. If you see. That is something.
What he's also trying to tell me now is that, sir, one transition may be used multiple times in the training because when I'm sampling from the replay buffer again and again.
Yeah. Yes.
Whereas in a real Q learning process, it doesn't get used so many times.
Yes.
Okay. Now coming to the last part of it, where we need the target network. That's the last thing I'll talk, and then I'll let go again. Okay. The idea is that every time I sample a batch and I do something, I may be undoing something which I have learned before. Depends on the set of transitions that I chose, right? You can think of it in this way. I'll make a rudimentary example. This is not precisely right, but still I think it will convey the point. Let's say I chose all 100 samples where the network actually took epsilon greedy algorithm based actions. Okay, which means those were not the optimal actions, right? Are you following me? If I chose all the actions which were trying to explore, right?
Yes.
So suppose my network tells me you have to take a right at this particular state. I may have chosen to go left just to explore.
Yes.
Right? All such transitions, if I choose and I try to train the network, what will happen? I'm looking for something new, but at the same time, I am overwriting something which I already know. My original Q value is being overwritten in some sense. And it is the balance between them that we are trying to figure out, isn't it? One part is what I have in previous memory, and one part is new exploration.
Yes.
So suppose in one episode, I chose all the transitions such that I was only exploring new, which means I have overwritten some of the old learning which I have had. Yes, at least partly I might have overwritten. not completely. Then
So these actions that these transitions that you are choosing from the reflay buffer, that transitions, it is erasing the learning that it has done previously. The network has done
yes, it
previously.
is affecting the Q value, no? So it is, when it is affecting the Q value, it is modifying at least whatever I have learned. I won't say erasing, it is modifying it definitely.
Okay.
Right? My question is, I don't want to see that modification go very haywire very quickly. I want you to learn at a slower pace so that I can keep track of my old stuff which I learned and keep improving upon it. So in order to reduce the volatility on the learning process, what I do is I create a target network which is a copy of the original network.
Okay.
Okay, and I update this target network less frequently. It follows my original model, but less frequently.
So there are these three things. So one is our reflay buffer from which we are sampling these transitions. One is this target network,
Correct?
which is not frequently updated as like
As the original network.
as the original network.
Correct.
Okay. So our aim is to make the
At the end of the day, the target network is what we will take as our final output.
okay, yes.
Okay, and in that network, I expect to see that y minus q should go to 0, which means every time I am at a particular state and I take a certain action, the q value corresponding to it should be the actual expected reward I expect to get out of it.
Yeah.
Okay, with that, I'm going to stop and let the authors come back to it.
Sir, one correction. So this target network is only used for providing stable updates during training, but the agent's policy that is given through the online queue network only.
Tell me again, Sanjeev.
No, sir. In the end, you said that this target network, this is what will be used to predict the, but that is not the case. This is just used to predict this target value in training. So it is just used to stabilize training, but like after the training is done, the online queue network, that is what gives the agent's policy. That's
Is it?
not the target network.
Oh, it should be the target network. Can you check
No,
up
sir.
on that?
After
No, it's
training
not
is
the
done?
target network. No, so this target network, it is just used to stabilize the training process. So after the training, only your online network will be used to give the policy. So,
That doesn't make sense to me, Sanjeev, somehow, because we are doing a soft update on the target network, isn't it? Which means
yes,
that it remembers a portion of what it had, and then whatever in the interim it has learned, we are updating it with it. So it would make sense that the final thing should actually be the target network.
no, sir, but it is not. We can even train without the target networks. Like, it is just
No,
used to.
without the target network, in which case the target network is essentially the equal to the original network. There is no difference between them. And every time step, both are getting updated. You can think of it like that.
Yes, sir. But if you see this agent's policy, it comes from the online network only, sir, not from the target network. I'm sure it is from the online network, not the target
This is
network.
during the training phase, isn't it? In the
Yes, sir.
final.
So the policy that the agent holds, it will come from its online network only, sir. The target network is.
Correct. It will come from its online network only. But after convergence has achieved, the policy should be the same between the target network and the online network.
Yeah,
At
if it
least
is
within a
converged,
certain
then
amount
the
of
target.
power.
Yeah, if ideally, if the loss has gone to zero, then, yeah, then both will be the same. In
Both
general,
should
it
be,
is the.
yeah, I would say that both are kind of similar within a certain tolerance limits. But you're
Yes,
right
sir.
that they won't be exactly equal.
Yeah.
Right? But by that time, what has happened that target network and the original network are emulating each other within some tolerance.
Yes, sir.
Right? That is the idea. So it really doesn't matter whether am I choosing the target network or whether am I choosing the online network. But I think notionally you are right that we choose the actual network to take on the job of doing any further testing and prediction.
Yes, sir.
Not
The
target
online network only always does that. So this target network is just used to predict the Q value during training. It just stabilizes the training like you told. Yeah, that's it.
Correct.
That's its only purpose.
But unless the two converge, then we are not seeing this temporal difference go to zero.
Correct.
Correct? All right. Okay.
So now I'll go how we are applying deep
Sanjeev,
learning.
I
Yeah.
had a question. So,
Okay.
is this different from DDPG?
Yeah, in DDPG you will have two networks, right? So in DDPG, the critic network it will be what the Q network is here, but the actor network it will be different. For the actor network will have a policy gradient loss, but the critic network in the DDPG will do the same thing that the Q network does, basically.
Yeah, so what's the difference here?
Yeah, so in DDPG it gives us continuous actions, right? So the DDPG in the critic network will take state and action as input and give the Q value as the output. So the loss function for the critic network will be the temporal difference loss, like we see here. But for the actor network, its loss is called the policy gradient for the DDPG. It will just take the state as input and provide an action as output, the actor network.
Okay, so there the target network is giving the action.
No, the actor network will give the action. So DDPG has two networks, as actor network and critic network, and there will be a target actor network and the target critic network as well.
So you can think of it like this, Ashwin, that in the DDPG algorithm, the policy is not being based on the Q value, it is not directly being taken, but rather a network is actually predicting the policy. A network is taking your values of the state as an input and predicting what the action you should take.
Yeah, and here what?
Here we are purely taking the action based on the Q value which is predicted.
Okay, only based on the Q value.
Sorry?
So in the Q network, it will just predict Q values for each of the actions that we have discretized for, and it will select the action with the maximum Q value. That's
Okay.
So it's kind of an extension of this to account for a policy where you can have continuous action spaces.
Continuous action.
Correct.
Okay, one more. How was the state space defined? Continuous.
yeah, our state space is continuous here, right? So I'll just go on it in a small amount of time.
Okay.
I'll talk about it. Yeah. Okay, so I'll go about how we are using deep learning for ship navigation. So, yeah, like Ashwin, this is our state space. So we have these four quantities in our state. So the course angular, this will be the difference between the desired heading and the current heading of the ship. The side track error is this perpendicular distance between the current location of the ship to the desired path, and the distance to the destination, that is another quantity in the state space, and the R rate is another one. So see, all these four quantities will be continuous.
One thing which I think even I was confused in the beginning, but I think I'm gaining a little more clarity. Course angle error is not with respect to the heading of the vessel.
Yes, sir. So yeah, we are not computing it with respect to the ship's positive longitudinal axis. Instead, we are taking it with respect to the velocity vector.
Correct.
Yeah, but it will be roughly the same unless there is a large amount of sway velocity.
Yeah, unless there is a large drift, you should
Yeah,
think of
large.
that to be similar. Correct.
Yes. Okay, and our action is the rudder command. So in DQN, the action can only be discrete. So we are discretizing the action, that is the rudder command to be minus 35, 0, or 35 degrees. So and this is how we are defining the reward. So three rewards are defined at every time step. So one reward is a function of the side track error. the other is a function of the course angle error, and the another is just a linear function of the distance. And at each time step, the agent obtains this reward. So it's just summation of these rewards, and if it reaches the goal point, terminal reward of a positive large reward of plus 100 is given as the terminal reward. So, and episodic reward is just the summation of the rewards obtained at each time step by the agent. So, and this is how we are training the agent. So our initial state is always the same, meaning so the ship is at origin, the initial heading is 0 and the search speed is 1, that is the service speed. And we choose the goal point at random instead. So it is chosen at a distance of 8 to 28 ship lengths, and the heading is also chosen at random. So the course angle error at the initial state can range from minus 180 degrees to 0 degrees. So, and these points are chosen at random so that like this agent sees different states in training. And the episode ends when it reaches the goal point, or if it like goes like away from the waypoint also, we have a termination condition that will stop the episode. Or when the maximum number of time steps for the episode is reached, that will also, the episode will end when the maximum number of time steps is also reached. So that is so. And these are some results after training. So as you say, the initial state is same everywhere. It's starting from origin with the same hitting angle, and it is able to reach destination points in different hitting angles. So this will have a course angle of 45. This will be minus 45. This is 135 and minus 135. So we are seeing that after training, it has trained uniformly in for different states. So that's so, and then say once we are sure that the agent is trained properly, so we can give multiple waypoints and ask it to follow a path. So in this left image, you can see that a path in the shape of an ellipse is defined. So it starts from this red point 10, 0, and it completes this ellipse clockwise basically. So and at one waypoint is given as the target, and once it reaches single waypoint, the next will be its target, and so on. So and this is another maneuver. So in this one, it completes the path in shape of nape. So basically it does this circle and then this circle. So,
Sanjeev, I wanted to ask something. I think I had forgotten to talk about this. When it misses one waypoint, do you still provide it the next waypoint as the target?
yes, sir. That's I do that. So yeah. So because if it misses, yeah, if I don't give the next waypoint as the target, it'll just circle back to this waypoint. So we don't want that. So,
So how do you know when to provide the next waypoint as the target?
so that is we define that in the termination condition. So basically, so there will be a line joining the waypoints, right? And imagine a perpendicular line passing through the target waypoint. So if the ship is crossing this perpendicular line and going, so we conclude that it has missed the waypoint when the distance between it is like greater than 0.5 ship lengths.
Okay, that is your negative termination condition. When it meets that, you just give the next waypoint as the target.
Yes, sir, and we say that it has missed this waypoint.
Okay, all right.
So these results are for calm water. So and our state space does not contain any wind parameters. So I just want to see how it performs when we give a when there are wind disturbances. So we just take a constant uniform wind acting in a single direction. So this capital VW is the non-dimensional wind speed. And this psi W is the heading direction of the wind. So we just take the relative components of the wind direction with respect to the ship's velocity, and then we calculate the forces in each direction as this one. And this Wx, Wy, and Wψ, this will be added to the right side of the equations of motion. So basically, so and this is how the agent performs when we give a wind. So in this image, you can see a wind acting in this direction the arrows are pointing. So basically, this is a heading direction of 0, and wind speed of a non-dimensional wind speed of 6 times the ship speed. So you can see in the between the first two waypoints, it is pushed away from its desired path, but it's eventually able to gain back on course. And the same thing kind of happens here. It's just a straight line path, but it is thrown away from its track between the first two waypoints, but it is able to gain back on course. So, and we defined a PID controller using the controller. This is just a simple PID controller, and this PID controller was tuned for this circle that you see here. So it was tuned for this circle of radius 8 ship lengths and defined by 17 number of waypoints. And we see that the PID performs as well as the DQN. I mean, it is slightly better than the DQN in this circle because it was tuned for this one. So, but we tried to reduce the radius of the circle, so this will be a much sharper path. So we noticed that when we reduce the curvature, I mean, when we increase the curvature, the PID was performing worse compared to the DQN agent. So.
How was the PID tuned for the circle?
Yeah, so we did it with Ashwin's help. So basically, we took the circle as the baseline. So we just tuned the gains until we were satisfied with its path that followed on this circle that you see for this radius of 8 ship lengths.
So like the at any position you are taking the say the normal along the normal to the circle, the distance between the your current position and the circle point.
No, what do you mean normal to its position?
I mean the error for the PID. How are you taking that error?
Yeah. So these errors are this is the same course angle error that I defined before. So yeah,
okay.
this is just defined on the same course angle error only, not the side.
So it is only based on heading, not on
Yeah.
the sidetrack error. The tuning of the controller for the PID controller purely is based on the heading. It is not using the sidetrack error at this stage.
But that is not fair comparison, right?
Yes, I would say so.
It is not using the sidetrack error, then how is it converging to the circle? Because only guaranteeing that heading goes to 0, the heading error goes to 0, that will not ensure, right? It will drag
Yes,
this.
that is true. No, but if you have sufficiently further away waypoints, then it will try to achieve that heading between the two waypoints. So as long as you have the waypoints finely discretized, it should be good enough. But if you have them too finely discretized, as you see on the picture in the right, you start to see doing haywire things. And the idea may be right that actually if you include the sidetrack error, it will definitely do a little better.
Yeah.
But here we were trying to see what is the limit or where the DQN can do it, but the PID couldn't do it. So that's what we were trying to actually find a counter example, and that's what he's trying to show you there.
Also, like the PID thing, like did the loop kind of thing also here in the right picture.
Yes, it did. And that's the question I have for Ashwin. Ashwin, when you are programming the PID controller, it also is looking at waypoints, right? One after the other.
Yes, sir.
So then.
So what happened here is you can see the loop one. When it reached the this leftmost one, always the point opposite to the starting point, it made a loop because it's based solely on the heading error, and it hasn't reached the termination point. That means the ship is not within 0.5 ship lengths, nor did the other angle termination condition also occur.
So, which means to say that when it reached the right-hand side part of the red curve,
it is just within 0.5.
So it is within 0.5, are there? I would think so. Beyond 0.5, no? No, my point is it must have missed this waypoint, correct?
Yeah,
Yes,
when it
I
misses
think,
the waypoint, it gives the next waypoint. And when it's configured to give the next waypoint.
Can you show it with that laser
Or is
pointer?
within 0.5 seconds.
okay.
Yeah, maybe Sanjeev, can you switch on the laser pointer on your mouse? And
Okay, how do I do that?
I think you have to go into slide screen only,
Yeah.
slideshow only, and then it will be there on the what do you call it? On the left bottom part of the slide, you'll see a panel when you are in slideshow. Yeah, under that. Yeah.
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 So I think if you see this point, it has missed this point too, but then it is tracking the next point. I'm not sure why this is making a circle around this point here.
No, that's what I wanted to understand, how it is programmed. So does it, the termination condition is the same as what is the termination condition for the DQN?
Yes, sir. So if it crosses this point with a tolerance of greater than 0.5 shift lengths, we consider it as missing this
Yeah,
waypoint,
so
so it
what
will track
happened
the
is,
next.
when it reached this part, it missed. So it is given next waypoint. But you can see that the heading, when it missed, is completely opposite of the target heading. So it looks bad.
So the around that loop, where is the point it missed?
That I'm not sure. It missed somewhere there. Then it decided to loop back given the next waypoint.
Okay, all right. That would be interesting to actually identify. At which point is it considered to have missed? Was it looking at was it on the outer side of the loop?
Yeah.
Towards the left. That is what I would think. Only then it would do a loop. Right? If it were not that much to the outer side of the loop, then it
Yeah,
would
it
have
would
tried
just
to
give
turn
the
the other
opposite.
way around.
Yeah,
It
the
would have
PID
taken.
controller would just make the rudder go the other direction and continue the zigzag maneuver.
Correct. It should have done that. But here I think the rudder might have already turned it around. Sanjeev, can you move your pointer to the left of the outer loop?
Yes.
Yes, slightly above. Further. I think that's where it might have missed.
Yes, it has to satisfy some band.
Yeah, it might have missed there. Only then it will do the loop. If it did any before that, I would have thought that it would take a turn the other way around.
Yeah, it should have turned this.
Yeah, see, if it had missed here, if it had missed at this point, it would have continued doing the wave. This wave, we don't
Correct.
have
This
to
wave portion, it should have done that. Correct. Okay, interesting. All right, we have to brace ourselves. This might come back on the review. Okay, good point. Is that it, Sanjeev? That's the last slide, or anything more to add?
Yeah, just some more about DDPGs.
Yeah, go ahead.
Yeah, so now I'll talk about this algorithm. This is deep deterministic policy gradient. So this is another deep parallel algorithm, but this can give continuous action. So as Ashwin was asking, this is just a simple extension of deep Q network for continuous action space. So this will have an actor network and a critic network. So this actor network, it takes the state as input and it provides an actions. So the actor's policy will provide an action, and the critic basically takes the state and the action predicted by the actor network, and it predicts the Q value for the action. So this critic network will perform the same thing that the Q network does in Q learning. So that is. So these are some results that we got with DDPG. And so now, so as you can see, like this left image, so the path followed by the ship is roughly the same for DQN and DDPG, but for DQN, the action space is discrete, so you can see that the commanded rudder can be minus 35, 0, 35 degrees. So the rudder variation is pretty sharp, but in DDPG, it can take continuous action, so you can see that the rudder variation is smoother compared to this one. And then in practical scenarios, we would want the rudder variation to be smoother. So that is so. Yeah, that is the end of the presentation. Next, we would want to try this other algorithm called proximal policy optimization. So this is called an on policy algorithm, and DQN and DDPG are both called off policy algorithms. So and this will also give continuous actions. And we can also implement collision avoidance in the RL agent itself. So, and we want to test these algorithms on the ASV at later stage as well. So that's the thanks. Any more
What
questions?
what would be the major difference between training a PPO and DDP?
Yeah, okay. So you see, DQN and DDPG, these are called off-policy algorithms. So we talked about the replay buffer, right? So what this does is it is called off-policy because when you transition, when you select from the replay buffer, you will be selecting samples which were given by a policy like what 100 episodes before also, right? That is possible. But by on-policy algorithm, what you mean is you will be selecting samples to update the network that are given by the agent's current policy only. So ideally, what you'll do is you will run maybe 30 episodes or 20 episodes. You'll get a number of transitions. You use these transitions to update the network, then generate again multiple number of episodes, then update the network. So that is why this is called on-policy algorithm. So understood? So,
Yes, yes. So the major difference would be the selection of the replay buffer, the transitions on the replay buffer. That is the
yeah,
major.
yeah. So this you won't say it as having a replay buffer. So that's the difference. Yeah, like it won't store multiple episodes till. So you'll just keep running episodes and then update the network using the transitions that you obtained with the current policy only. So in DQN and DDPG, when you have a replay buffer, so when you select random transitions, you'll be using transitions that you might have used 100 updates before or 200 updates before, right? So that is a that transition was given by a different policy, right? That's right. It's called off policy.
Okay, okay, okay.
So why is a PPO found to be better than DDPG or something?
Uh, yeah, so basically, from what I know, so in these DDP, it's a policy gradient method, right? So in policy gradient methods, I think convergence is pretty hard because this policy gradient loss is you won't limit the step size, but in PPO the difference is your loss function. They'll define a loss function and it will be limited to a certain value. So the updates are supposed to be more stable in PPO. That is one thing.
We actually know what is the difference between them once we implement them and compare, isn't it?
Yeah.
Also, the DDPG and like in the DDPG there is that actor and a critic, right? So is it
Correct.
some? Can I say like the actor is essentially like ultimately trying to copy that entire critic's role?
No, not exactly. So these two have different tasks basically. So this actor, this will just give the action. So and this critic will evaluate how good the action is. So both these networks will keep getting updated once you update. You'll be updating both networks basically.
And when do I say that it is like getting better?
Yeah, again, like you'll be, yeah. So you can say that once your loss is going to zero, or in RL, basically, instead of seeing the loss curve, you'll see the reward versus episode curve. So the reward curve should flatten out, basically. Yeah. Then you'll know it has converged.
So the actor's reward curve is what you will be looking at.
Uh, no, so basically, the actor will have a loss and the critic will have a loss. So you can say that when the critic loss goes close to zero, it has converged, or by reward, you mean the agent has reward. So there's no separate rewards. Reward is just common for both.
Okay, okay. So critic's loss is your determining factor.
Yeah, it will be.
All right. Any other queries? All right. If not, let's thank our speakers for the excellent presentation. That was a very detailed overview of reinforcement learning and different types of reinforcement learning. They've actually submitted a paper on this topic just now. So So just last evening they have submitted a paper for the Journal of Engineering Applications for Artificial Intelligence. So we'll be waiting to hear back the reviews and hopefully get it published soon enough. Next topic, as Sanjeev has said, we'll be trying to look at different algorithms, and also my main motivation is to get him to implement this on the actual ASV and see what happens. That would be so cool to observe. All right, let me stop recording. We don't have any other queries.